You know that feeling, right? You're on a super important video call and boom, everything freezes. A little box pops up blaming bad network quality. It's so frustrating. Well, today, we're going to pull back the curtain on the powerful tool that prevents that exact problem. Quality of service, or as you'll hear it called, QoS. Let's dive into how this tech brings some much-needed order to our chaotic digital world. To really get our heads around QoS, let's start with an analogy. Just picture a big 4-lane motorway. You've got all kinds of vehicles, cars, buses, big trucks, and on a good day, when traffic is light, everything just flows perfectly. It's a great system when there's no congestion.
But what happens when rush hour hits? A total standstill, a traffic jam. Now, for most of us, that's just annoying, right? But for an ambulance trying to race to the hospital, that same traffic jam is a critical life-or-death situation. It absolutely cannot afford to be stuck in line with everyone else.
Okay, so that motorway, that's your network. And every single car is a little packet of data. And just like with real traffic, not all data packets have the same urgency. When your network gets clogged up, you get a digital traffic jam. And some really important data can get stuck behind the digital equivalent of someone looking for a parking spot.
And this slide just nails the problem. Think about it. If opening a website takes an extra 100 milliseconds, you're not even going to notice. But on a voice-over IP phone call, that exact same 100 millisecond delay is the difference between a crystal-clear conversation and a choppy, garbled mess where you can't understand a thing. Your phone call's data is the ambulance. The website data is just a regular car.
So, how do we fix this? How do we build that special emergency lane, that HOV lane, on our digital motorway? Well, this is exactly where quality of service comes into play.
At its heart, QoS is basically a set of rules that tells your network gear, your switches, your routers, how to treat different kinds of traffic. It classifies the data, figures out what's important, like our ambulance, and makes dead sure it gets priority. Everything else, it gets handled on what's called a best effort basis, which pretty much means we'll get you there when we can.
So, how does the network actually enforce these rules? Well, it uses special markings, kind of like digital tags, on the data packets themselves. The three main rules of the road we're going to talk about are class of service, differentiated services code point, and Wi-Fi multimedia. Okay, let's start with wired networks. You've got class of service, or CoS. It works at layer 2. Think of it like a local traffic rule that only matters inside a specific neighborhood, or what we call a subnet. As soon as that data leaves the neighborhood, that CoS tag gets stripped right off. DSCP, on the other hand, is a whole other level. It works at layer 3. It's more like a permanent sticker on the vehicle's license plate that stays with the data packet as it travels across all sorts of different networks and routers. It's much more persistent. And this table here shows how QoS assigns priorities. It's a really simple 0 to 7 scale. You'll notice the highest values, like 7, are actually reserved for the network's own control traffic, the stuff that keeps the network running. Then you see voice over IP, or VoIP, getting a nice high priority of 5, while your everyday web browsing, that falls into the best effort bucket with a priority of 0. Now, DSCP is way more granular. It gives you 64 different values to play with, so you can create much more complex rules. You see that top one, EF, which stands for Expedited Forwarding. It's basically a VIP express lane that's almost exclusively for voice traffic. Then you've got assured forwarding for things like video conferencing, guaranteeing its delivery, and yep, standard traffic again gets the default.
And what about wireless? You could argue QoS is even more critical over Wi-Fi. Wi-Fi Multimedia, or WMM, keeps things simple. It breaks everything down into 4 main categories: voice, video, best effort, and background. And the cool part is, your wireless access point is smart enough to see these categories and translate them into the right QoS and DSCP values when that traffic hops onto the wired network, so you get a totally seamless experience. Okay, the theory makes sense, but how does a network admin actually put all this into practice? Let me tell you, it's not about just flipping a single switch. It's a really careful, multi-stage process. A proper QoS rollout involves these 5 key stages. First, and most importantly, you have to audit and plan. Then, you configure the individual access ports where all the devices connect. After that, you move to the uplink ports between your switches. Then the main gateway or firewall. And finally, you have to monitor and verify that everything is actually working the way you thought it would.
And I'm telling you, stage 1 is everything. You absolutely cannot skip the planning phase. You have to know what applications are running on your network, you have to figure out which ones need priority, and then you've got to do the math to calculate how much bandwidth they're actually going to need.
Let's look at a quick real-world example. Say you have 10 people who might be on a Microsoft Teams call at the same time. Each of those calls uses about 3 megabits per second. So, 10 times 3, that's 30 megabits total. On a standard 1 gigabit connection, that's only 3% of your total capacity. So to be safe, a good admin would probably allocate a reserve 5% of the bandwidth just for those Teams calls.
And this right here is how all that planning translates into actual configuration code. This is for a Cisco switch, but the idea is the same everywhere. These commands are telling the switch, hey, when you see VoIP traffic, I want you to tag it with a DSCP value of EF and a COS value of 5, and, most importantly, give it a guaranteed priority of 5% of the bandwidth.
Now, here's a subtle but really vital detail. The priority command you see, that's a hard limit. It guarantees that 5% is always available for voice, but it will drop any voice traffic that tries to use more than that. Why? To protect the rest of the network from being starved out. The bandwidth command, though, that's a soft limit. It guarantees 5%, but lets the traffic use more if the link isn't busy. It's a crucial difference.
So, looking at all those steps, all those lines of code, you might be asking yourself, is all this complex work really worth the effort?
Oh, 100%. Absolutely, because it represents a huge shift in how you manage a network. You're moving away from a simple, best-effort, first-come, first-served free-for-all to an intelligent, intent-based system that actually supports what the business needs to do.
I mean, just think about this. The vast majority of IT help desk tickets, they aren't about things being completely broken. They're about things being slow. Glitchy calls, laggy video conferences, slow apps. QoS gives administrators direct, granular control to fix these performance problems before anyone even notices. So at the end of the day, while most of your users will never even know what QoS is, they definitely feel its effects. And for system administrators, it's one of the most powerful tools working quietly in the background to make everyone's lives easier and to make those frustrating ticket queues much, much shorter.
And that really leaves us with one final thought. By default, your network treats every single piece of data, from a critical business call to a cat video someone's watching on their lunch break, with the exact same level of importance. After seeing how QoS works, the real question is, should it?